All right, thank you for the introduction, Rak, and thank you for the organizers for the invitation to this stimulating workshop. I look forward to discussing all of these very exciting topics with all of you in the next few days. So what I'll be talking about today from the title of my talk is machine learning, these particular topological invariants for certain classes of three manifolds. Now, Songjin has thankfully introduced some of these concepts, so I don't have to dwell too long on these. But I'll still do so just to kind of motivate why I'm kind of choosing to train the certain architectures that I have for the tasks at hand. So just as a brief kind of overview, this Z-hat invariant is relatively new. It's really been defined in the past 10 years or so. And there's been a lot of excitement around it because it originally was defined in a physics context, and I'll cover that a bit in order to get us all on the same page in a moment. But it has intimate contact with various topics in mathematics as well. So as I kind of alluded to, this is deeply connected to three-manifold topology and plays an important role in Heegard-Floer homology, in knot theory through its generalization with FK invariants, and has potential applications in potentially giving us some window into the homology cobordism group. That's kind of an ongoing project. This also in the recent past has been explored from the context of number theory. So the groups, including Miranda Chang, who's my advisor at the University of Amsterdam, has been instrumental in understanding these Z-hat invariants in the context of number theories through the objects known as quantum modular forms. I'm not going to talk too much about these kinds of topics. I'm mostly going to be concerned with the first two, the top two topics, so topology and physics. But this is just to kind of motivate us all to think that there's a lot to explore in this very new object, and there's been a ton of work that's been done recently. So I'm going to give a very brief overview of the physics definition of this object, and it's not going to do it enough justice to I don't know, really give you the full picture of it. But as with all things in physics, we start with M theory. So that is, we take a stack of M5 branes on this 11-dimensional background where R is some time-like direction, Tn is a Taub-Nut space, and we have the cotangent space to some compact three-manifold M3. We could possibly decorate this with a defect network with intersecting branes, but we're not going to be that adventurous here. This is just going to be the plain vanilla case where we only have a certain number of coincident M5 branes. And the world volume theory of this, when zooming in on these M5 branes, is a six-dimensional n equals 2, 0 theory. In this case, there are ADE generalizations. We're only going to be concerned with the A series. So we can consider just 60 AN minus 1 n equals 2, 0 theory. That the background on which that theory is defined in this embedding is this product space of this compact three-manifold M3 and then some other three-dimensional space. Now, this kind of factorized form allows us to perform various topological twists and reductions to give this kind of a beautiful three-dimensional duality. So if we perform a topological twist on M3, and there are various types that one can perform. In this case, I'm just thinking about the classic one from Demofte, Gaiato, and Gukov, where we preserve n equals 2 supersymmetry in 3 dimensions. Reducing on M3 produces a generically interacting theory on W3. We call this theory TM3. If we go the other way and compactify and reduce on W3, we end up with a topological quantum field theory on M3. And so there is, in this 3D correspondence, a notion that the supersymmetric localized partition function of the TM theory on W3 is in correspondence with the topological invariance or homological invariance of the manifold M3. Right. So to make this a bit more clear, if we consider W3 to be the cigar type geometry, and for the rest of the talk, we'll fix the gauge algebra of the 6D theory to be SU2. So we're just in the A1 theory. You can generalize to arbitrary n, but there are limitations that we have with that as well. So fixing that geometry and that gauge group, we have this correspondence. So we have the supersymmetric localized partition function of TM3 on this cigar geometry, where we've compactified the time direction as well, such that the boundary of W3 is a torus. And since this space has a boundary, we need to specify supersymmetric boundary conditions that we label by this index A. Now, in the 3D correspondence, this is one-to-one correspondence with the abelian flat connections, the abelian SU2 flat connections on M3. So there's that this is how you get from the physics, the BPS physics of the 2D, 3D system to topological and homological invariance on M3. So when we define this modular parameter tau and this fugacity e to the 2 pi I tau, we have a definition of the supersymmetric partition function in terms of this counting function of this on this bigraded Hilbert space. The bigrading is done by the U1 times U1 symmetries of the tau-nut manifold. And so what we end up with is a statement where the this is so on the left-hand side, this quantity is related to what's called the half index of the theory. That is, there is some overall prefactor related to the supersymmetric Casimir energy times a counting function. That counting function is the superconformal index of TM3 on this background. And so on the right-hand side in the topological quantum field theory, we just have this sum over this, or this weighted graded sum over the dimensions of these graded Hilbert spaces. And so this gives us a kind of natural correspondence between the BPS physics here and a counting function of the dimensions of these homologous spaces. So the right-hand side can naturally be seen as peeling off some leading power of Q. This delta is a kind of an important quantity in the study of Z hat, but it won't play so much of a role in what we discuss. The important part here is that what you end up with is an integral series in Q. So this is extending, as Sung-Jin alluded to, this kind of WRT invariant is analytically continuing to the interior of the disk, and inside the boundary of the unit disk, we get this expansion. So this is normalized so that these integral series start at Q to the 0, and the first coefficient is 1. Now that again has a mirror in the index on the left-hand side, where the first term that you should find in counting BPS states is the lowest dimension operator with no other quantum numbers, the identity operator, which must necessarily be unique. So there's no multiplicity there. How? Yes. Yeah.
Tau-nut is a transport space of 5M5, right?
Yeah. Okay, so following the definition of Z hat in this original formula, or in these original papers, there was a notice, well, Miranda and some friends noticed that there was a manifestly modular property that Z hat obeys. So there is some action of SL2Z on these Z hat invariants that kind of organizes them into a family. And so there are organized an orbit of equivalent Z hats according to SL2Z actions. And this will play a role in some of the experiments that we run. Okay, and as Sung-Jin had also kind of foreshadowed, there is not a generic mathematical definition. So this kind of physics definition holds for arbitrary 3-manifolds, but we don't always know how to compute the superconformal index, the half index, or Z hat for an arbitrary M3. It is only in the case of weakly negative definite Plumbed 3 manifolds that we have a strict mathematical definition. That is, the weakly negative definite condition means that in the linking matrix M on the space that's spanned by the high valence nodes, that the inverse is manifestly negative. And so the object that we'll be studying is essentially this very nice contour integral over some theta functions. But since we're putting this into very simple MLP networks, which I'll describe in a bit, that contour integral form isn't very amenable to putting into a machine learning platform. So what we have available to us is harkening back to that notion on the previous page, where we wrote down this kind of sum over the dimensions of these vector spaces, and we performed this expansion in Q, so in the interior of the disk. And so what we're going to be studying are these, yes. M is the linking matrix of the plumbing graph. So that means the high valence node. So this is only looking at the subspace that's spanned by high valence nodes. So you kind of do some kind of reduction onto that space. So that's the weakly negative definite case. So I mean, if it was strictly negative definite, then it would be the entire matrix. Yeah.
Does it mean that the base manifold defined is corresponding to X2 times S1?
No, not necessarily. Like I said, we have this cigar type geometry, so the boundary manifold is not necessarily just the disk, right? You can, so very importantly, these can be used to reconstruct like the S1 times S2 partition function. What it would correspond to is taking pairs of these Z hat invariants and then gluing them, so doing orientation reversal and then gluing them together, and then summing over all of the possible gluings for all of the possible supersymmetric boundary conditions that are contained in the set A. That way you would get back together the superconformal index of TM3. Right, so these are kind of like holomorphic or blocks of that index. Okay. L is just a vector in this lattice. T to the Z to the L. I mean, that's this. Those are these quantities, right? So you can see those are just basically it's a product over the let's see. So these are the integral variables that are defined over the vertex set of the plumbing graph. And this is just a vector of all of them taken together raised to the L power. So, but okay, so this isn't going to be entirely important. What is important is that there's an expansion in this form. So all of the data that we're going to be studying is going to be coming from this Q series expansion. Now, since we don't have the capacity to input infinite series into some kind of machine learning platform, we're going to have to suffice to truncate these Q series expansions. And so the choice of cutoff is going to be important because that will kind of tell us exactly how much of the original Q series that we're studying, and that will get us closer to a form that can realize some of the modularity properties. Now, strictly to realize modularity properties, you need every single term in that Q series expansion. So it won't be manifest, but as you continue to add terms, you're getting closer and closer. So we'll choose generically very large cutoffs for this. So one point to note is that as we increase the number of high valence nodes or the rank of the gauge group, or if we're to deform the theory by adding Wilson lines, that greatly adds to the computational complexity of computing either this contour integral or the Q-series expansion. And so we're going to have to limit ourselves to basically two classes, and I'll describe them in a bit. But there is recent code by Davide Pissarro, who's part of this collaboration, that claims to, in a Cythonic way, computes Z hat and these Q-series expansions. So there is a bit of a speed up, but some testing still needs to be done on this to recover some known results. As I mentioned before, also that we're going to be doing some experiments with these SL2Z orbits. Mainly, we're going to be seeing if a network can actually learn the size of an SL2Z orbit. The problem is that only in a handful of cases is there an actual analytical formula for the dimension of this orbit. This is, of course, infinite class, but this is the only known case where we have a Breeze-Korn sphere or a Seifert manifold that has a determinant of its linking matrix being unit modular, such that its Seifert data is mutually coprime and square free. In that case, we just have this very simple formula related to the Milnor number of the three manifold. But apart from that, there are only a handful of sporadic cases where the SL2Z orbit has actually been computed. And so those can represent for us some out of distribution data that we can use to test any generalization of the networks that we train. Okay. So that's the basics of the quantities that we're going to be using as inputs. But as a bit of a motivation for the questions that I'm trying to ask is, within these Q series, there is some data there are some properties of Z hat that are lost. Like I said, modularity requires an infinite number of terms in order to be manifest. And so beyond that, this Z hat is one representative of an infinite class of three-manifold invariants. And so finding the structures within Z hat that can distinguish it from other topological invariants, or I mean, it's a very important problem. And so what we're going to be doing is a set of classification experiments that are going to be trained on this Q series data. So the pipeline, it is going to be entirely supervised learning. So everything that we work with is labeled data. I'm not doing anything nearly as fancy as what Sungjin and Pavel did. So what we're doing is taking the Q series data that is represented by a string of integers, including all possible zeros in this case, and labeling each vector in that by whatever we're going to be using in the classifier. In some cases, I won't be talking about this within this talk, but in some cases in the paper that will be appearing hopefully at the end of the month, we also test some of the results that we do find by changing the kind of input representation of the data, including passing through some kind of auxiliary contrastive learning network in order to kind of learn from the latent space. So what we do, we're just going to follow these solid lines. We're going to take the generated data for Z hat as much as we can get, and pass it into a classifier network. Now, this classifier network is just going to be a simple, fully connected feed-forward network, just a multi-layer perceptron. And it's going to be fairly shallow and fairly narrow, because increasing either of those hyperparameters doesn't seem to add any benefit. So I'll describe the networks in the following slides. But once we have the outputs of these classifier networks, prior to any softmax or argmax labels, these logits of the network, we take two paths. Either we pass them through the softmax and argmax layers in order to get the classifier and its performance, so we can assess it by looking at the confusion matrix or whatever the balanced accuracy score, whatever metric we have for assessing whether or not that classifier was doing its job. Once we have a classifier that is performing very well, we take the logits and then we pass them through a regression network. So the question that I've been trying to answer recently is, say we train a classifier that is performing very well, that has over 90% accuracy, and can distinguish whatever labels that we're giving it. The question then is, what within Z-hat is actually being learned? What are the pieces of data that we can use that are actually being used by the network in order to make the decision boundary in the latent space of the logits? That's actually a pretty difficult problem to solve, but there are some tools, and the rest of this pipeline is dedicated to that. So the logic of the experiments are the following. Once we have the logits, we then use those logits as a target space for a regression network. Now, what's input to the regression network are various features that we are going to construct. I'll explain this in a bit later, but it's stuff that is computed either from the Q series itself or the linking matrix. So once we have this feature space that we're trying to fit into the logits, we pass them through the progression network, then we take those outputs, and then we do a series of data analysis experiments on them. So at the end, we come up with a set of statistics that tell us exactly what are the important features that are being learned by the network in order to make its decision, and what are the most robust features. Now, these are two separate questions, and the interplay of answering them is actually kind of fascinating. So without stalling any further, I'll just ask if there are any questions regarding the logic of what I'm doing. Okay. So to walk through each part of this pipeline, first we limit ourselves, as I mentioned, to choosing a fairly low number of high valence nodes. That is, we only consider 1 and 2 high valence nodes. So star-shaped graphs that have a single high valence node and then an arbitrary number of legs that are emanating from it, and 8-shaped graphs, which have 2 valence 3 nodes, 4 valence 1 nodes, and then an arbitrary number of valence 2 nodes in its graph. And as I mentioned, the computational complexity for computing Z-hat increases. So we can compute the Z-hat to very, very high orders very quickly, on the order of 10 to the minus 3 seconds for star-shaped graphs, where it'll take perhaps 10 minutes to compute some of these. So going to much higher number of high valence nodes is not really feasible for these kinds of experiments at the moment. So within these two classes of plumbing graphs, we have 2 additional kinds of labels that we attach to them. And that is whether or not the manifold that these graphs are plumbing are homology spheres or not. So we have 2 binary labels, sphere and non-sphere, and star-shaped and 8-shaped graphs. And within that data set, we have over 58,000 examples of Q series for Z-hat computed out to a cutoff of Q to the 10 to the 4. So this has a very high cutoff, but that's necessary in order to capture enough non-zero coefficients in these Q series. So as I display here, the vectors that are appearing in this data in each one of these rows is a vector that has 1 at the beginning, and then perhaps a string of zeros, and then a non-zero entry, and then perhaps more zeros that separate them. So I refer to this as the sparse representation because, in particular, for these star-shaped graphs, even going out to Q to the 10 to the 0 or to 10 to the 4, we can have maybe 4 or 5 non-zero coefficients. It's very sparse data. Right. So in the data sets, we also have these very particular Brieskorn spheres that have 3 singular fibers, for which we can compute the size of the SL2Z orbit. We have to increase the cutoff significantly to q to the 10 to the 7 because we have to sweep over rather large numbers within this data set in order to generate these 5,000 examples. We then also have some of these out of distribution tests for that set of experiments. Okay. So with that data, we then pass that into the classifier network. So these are deep in, well, 4 layers deep. Everything is summarized in this table here. 4 layers deep and between 32 and 64 nodes wide in each hidden layer. So these hyperparameters were tuned just through kind of experiment to see which was going to give me the best accuracy scores. So we split the tasks up into a set of binary classification tasks, and then we further subdivide those based on some of the other labels. So in these experiments labeled by top, what we're doing is classifying the graph topology, whether, is that right? Yes, yeah. So we fix the homology class of the 3-manifold, either it's a sphere or a knot, and then we're trying to classify whether or not the Q-series data that it's seeing is coming from a star-shaped graph or an H-shaped graph. On the other side, we have fixing the graph topology to be star or H, and we're classifying whether it's a sphere or not. So this first row here, hom star, is fixing the class to be a homology sphere, or I'm sorry, is fixing the class to be star-shaped graphs and then classifying whether it's a homology sphere or not. So we also try to test the robustness of any of the learned features that we have by being, instead of fixing, say, the graph topology or the 3-manifold homology, just being agnostic about it, using the entire data set, and then rerunning the binary classifier of H-shape or star-shaped or sphere or non-sphere. And as you can see, these networks perform very well. They're very simple and they're not very wide, given the fact that what's being input into them is a 10,000 dimensional vector. It compresses the data very well into this kind of binary label. So we have these balanced accuracy scores because they are generally unbalanced data sets. So we see that they're generally performing such that the balanced accuracy score is well over 90%. So these are all good performing networks that we then extract their logits and pass into the regression networks as the kind of target space. So in order to explain what those classifiers are learning, we take the logits, pass and use them as the target space for these simple multi-layer perceptrons. Here, again, these are just completely connected feed-forward networks between 2 and 4 layers deep and between 32 and 128 nodes wide in the hidden layers. There needed to be a bit more fine-tuning of the hyperparameters here because the regression problem is much more difficult than classification. So what we do, so even though the space in the logits is linearly separable and the logits typically lie on some quasi-linear subspace in this two-dimensional label space, linear regression did not work. It did not perform, it did not give us a very good fit, which is why we went to these nonlinear regression networks. And so what we're trying to do is learn to see if the network is using either data from the plumbing matrix, so the linking matrix. So the data that we can derive from that is the determinant of the matrix and the spectrum of its eigenvalues. Here, we're just going to take the minimum and maximum eigenvalue and the mean and standard deviation of the eigenvalues as data that is implicitly seen by the network. Because if you recall, what appears in the exponent in this theta function is the inverse of the matrix. So there's going to be something in very, very abstract about the linking matrix that this network can see. There's also kind of explicit information that it has seen, and that is from the Q series itself, either the maximum coefficient or information about the gaps between non-zero coefficients. So these are the gaps in the exponents. Gamma 0 is the first gap, so from Q to the 0 to the first non-trivial entry, and then the mean and the standard deviation of the gaps are also implicit, or rather explicitly seen by the network. And so we train these regression networks and they perform fairly well. The lone outlier, strangely, is this Ham star case. This was the best performing network that we found. The Pearson correlation score for the logits, which is just kind of measuring the kind of linearity of the fits, and the R squared, which is giving us the explained variance of the fit for the ground truth. Those scores are a bit low in the 70s and 80%, where everything else is, in the high 90s. I do not have an explanation for why this is the case, but what we'll see when we pass through the data analysis, this actually gives us one of the clearest answers to what is being learned. So something strange is happening here. Once we pass through the regression network, we have a set of outputs, and we have these scores. And so we need a way to characterize exactly what is being learned. What is the feature that has the highest weight and is the most robust to any kind of perturbations? So for that, we employ a three-mode strategy, where first we compute the Rak-Kyeong saliency. What this is just this is called the gradient weighted class activation mapping. So all this is doing is taking a given feature and then compiling layer by layer all of the weights. And then you take all of the weights together and apply some nonlinearity to get this localization map, LX, and that can be visualized very nicely in this heat map. So this is telling us what the network is weighting most highly from the input to the output. But that isn't always a sufficient diagnostic for what's happening within your network. Because this is just giving you a snapshot of a single instance. You're not getting any kind of statistical information about the importance of any of these features. And so we also employ this permutation importance analysis, where this is literally just taking any given feature and breaking the correlation between the inputs and outputs by randomly permuting the rows in a column. There are some limitations to this approach, which is why we use another one. So you can imagine that if you have very highly correlated features, varying one column is going to potentially degrade the performance of the network. Is going to be correlated with the degradation of the performance of the network when varying another column. So the relative importance between those two features may be suppressed. And if you have anti-correlations, then it may actually boost one of them. So this gives us a kind of a nice picture by giving us a tool to permute, to break these correlations and then run those experiments over and over a large set of training runs in order to get some statistical information as to which is the most important for a model. But that there are important caveats to relying solely on that, which is why we also use these kind of newer techniques by computing the Shapley values for the network. I won't go into too much detail here, but these Shapley values come from coalitional game theory and are a way of assessing the payout to an individual agent within a game, within a coalition. So you can think about the application of this to neural networks in a pretty easy way. So you have some output of a network that scores very well. So you give it some metric for determining how well the network is performing. And then you ask, if I form a coalition between a subset of my features, what is the payout that the network receives? What is the score that the network receives? And then doing that by permuting over all possible coalitions, you then get a picture of exactly which is the most important, which has the most impact on the performance of the model. And those are kind of ranked in this B-swarm plot. So the top row being the most important. And you can see that there's generically an agreement between the permutation importance and Shapley values. And we'll see that across the board. But there are going to be cases where there are deviations, and those are very interesting. So these are 3 different kind of techniques using to assess the suitability of a regression network and finding which are the most important features. So taking from the regression results that I had on a previous slide, the outputs of those networks are then passed through this data analysis pipeline. And what we see is something rather interesting. So in Ham star, we have that the gradient saliency analysis, the permutation importance, and SHAP analysis give us the same kind of winner across all, and that's the minimum eigenvalue. And that's something that we can actually understand because the network is trying to classify between homology spheres and non-spheres. And what distinguishes them at the level of the linking matrix is whether or not the determinant is 1 or -1. Right? So if the determinant is plus or minus 1, it's a homology sphere. And if it's not plus or minus 1, it's not a sphere. Why it's learning the minimum eigenvalue is that the determinant itself is not a very descriptive feature from the perspective of the network. Instead, it learns the minimum eigenvalue because if the determinant is 1, then there is a small, at least one small eigenvalue that can be written as the inverse of the product of all the other eigenvalues. And so the existence of a small eigenvalue that's orders of magnitude smaller than all of the other ones tells you whether or not it's a homology sphere. How am I doing on time? Okay, yeah. So I'll be brief to this. Okay, so it's actually learning something that by eye you can understand why it's learning this. Although, funnily enough, as Sungjin mentioned, the determinant is invariant under Neumann moves. The eigenvalues are not. So it's learning something that is not an invariant in that case. So it's something interesting is happening here. But what I want to focus on right now is this Ham-all. So this is being agnostic about the graph topology, using the entire data set and then asking homology sphere or not. Because here, what we see is that it's not learning the minimum eigenvalue at all. That's not very highly weighted in any of these analyses. But what is highly rated is the standard deviation of the eigenvalues, the mean of the eigenvalues, and the maximum eigenvalue. Now, why is that? Well, if we look at the correlation heat map of these features, we see that they're very strongly correlated with one another. And in fact, if you do a very simple ablation study where you just try to retrain networks using only the standard deviation as of the eigenvalues as an input, it performs very poorly. And if you use any of these others, it will also perform very poorly. But if you add them together in this coalition, it explains almost the entirety of what's being learned by the network. So why it's using this information and not what we would expect as either the determinant, which is scoring very low, or the minimum eigenvalue as its stand-in, is kind of a mystery. So it may point to some invariant that is hiding within the statistics of the eigenvalues of the linking matrix. And why I say that is because when we perform the other classification experiment, classifying graph topology, having fixed the three-manifold homology class, when we are agnostic about it, using all of the data that we have available to us and just asking star-shaped or H-shaped, the SHAP analysis and the permutation important analysis tell us very similar stories as in the previous experiment. And the gradient saliency is a bit different, but it still weights the standard deviation of the eigenvalues very highly. And in fact, the SHAP analysis gives us almost the exact same output when doing this binary classification. So it's asking a completely different question, trying to classify different data, like a different divided data set, and it's giving us the same kinds of results. So that's why I said that there might be something to these quantities that hasn't been appreciated in the math literature before. For the other experiments, there is what we see is that the data concerning the gaps are most important. So the first gap, the mean and the standard deviation of the gaps rank most highly. And that kind of makes sense because, as I said, the star-shaped graphs, their Q series are far sparser than H-shaped graphs. So the gap data is very, very different between those data sets. So the fact that it's grabbing onto those is understandable. So the takeaway from from these experiments is that I think there's something that we need to explore within the eigenvalues, which, as I say again, are not invariant under Kirby moves, but are important to these networks. So there's something hiding there. Okay, so in the last couple of minutes, I'll move on to the other set of experiments that we ran. These were learning the size of the SL2Z orbits. In this, we changed the representation of the data slightly. So we had in this first set of experiments, just again, a 4-layer multi-layer perceptron with 32 nodes in the hidden layer. But instead of inputting all of the like every single coefficient, even if it's 0, we compress it into this kind of dense representation where we've done this positional encoding where the arrays are now the coefficient and then the position that it appears in the Q series arranged in a tuple, and then you have an array of those tuples. Now these get padded when we're passing it into a multi-layer perceptron because all of the arrays have to have equal length. So we just do some 0 padding to the right for all of the shorter arrays. And so when we pass it into, so when we pass the Q-series data for these class of Breeze-Corn spheres into this MLP, we get a fit to alpha, the size of the SL2Z orbit, that's incredibly good. It explains almost all of the variance in that data. Of course, it's in this space just a linear space, so it's not too surprising. So when you do a linear regression on the outputs of that multi-layer perceptron, you see that it's learning almost exactly alpha, and with some irrelevant offset. So when we then look at the gradient saliency analysis for this network, what we see is very interesting. So when it's input into the input layer of the multi-layer perceptron, we unroll these tuples such that the first 128 entries are all coefficients, and then the last 128 are all of the exponents. So it's just taking coefficients, then exponents. What this is telling us in this gradient saliency analysis is that it's paying attention. This is actually the 128th entry. So this is paying attention from the first exponent all the way out. So to this network, what was most important was not the coefficients, which is also not very surprising because for these Breeze-Corn spheres, all the coefficients are 0, are 1 or -1. And so it's giving us some interesting attention on the exponents. But since we kind of packaged everything in this dense representation, I just did a very silly kind of experiment, I asked, instead of passing it to an MLP, what if I gave it without any kind of zero padding, just this group of ragged arrays, but just pass that to a transformer network because they don't require any padding. And so I just wanted to see if that could perform similarly. So I just coded up a very simple 2-layer MLP for the embedding, and then used 4 attention heads on the transformer network. So this is very simple. There's not a whole lot going on here. But we see that it actually performs on par with the MLP. Although it takes a lot longer to train, it still gives us a kind of linear relationship. I can't explain exactly why this shift went from +4 to -500, but the important point is that it's still learning this kind of linear relationship between the Seifert data and the outputs. What's very interesting, though, is that the saliency analysis for this network shows something very, very curious. So it's again showing us that the exponents, because we learned that networks are learning exponents, the early exponents are the most salient. But what was really curious and was noticed in this last week in a workshop in Taipei that Rak was at, there is this kind of quasi-periodicity that's appearing in here. I thought that may have just been kind of a quirk of training this transformer network. It's kind of hard to tell exactly what's happening inside of it, but it was noticed that the quasi-periodicity is mod 8. And so this past week, we kind of hit on an explanation for this. This seems to be a real feature because if you look at the Z-hat Q series for these Breeze-Corn spheres, they're expressible in terms of an octet of false theta, or not false, partial theta functions of the following form. And what we were able to see is that these exponents naturally organize themselves into groups of 8. And so what's happening here is that the quasi-periodic structure that's being learned by the transformer network is being reflected by, is a reflection of the quasi-periodic structure in these partial theta functions. So the transformer is paying attention to specific partial theta functions as it's scanning over, as the attention heads are scanning over the data. Now the question is this robust, right? Is this actually something that is, we're kind of convincing ourselves because we want this to be true and we have a nice explanation? Well, it turns out if we reinitialize the network again and again, we get the same Z8 quasi-periodicity over and over. So this is something that is being learned by the network. So that's kind of a fascinating result because this is not obvious. This is not typically the way that you would write the Z-hat expansion. So it's very curious that the transformer network actually learned this. And so with that, since I am out of time, I will leave this slide up and I'll thank you for your attention.